Good evening. So our speaker is Igor Khavkine from Prague. I think it's time to begin. So Igor, you're welcome. Well, and I hope you will be understandable to everyone.
Thank you very much for the invitation. I like this seminar, and I'm glad I have a chance to talk about some recent work here. Let me share my screen. And I hope everybody will see the slides, full
Yes,
screen and so on.
yes.
Yeah, so please feel free to interrupt with questions if you have any. I will discuss basically the contents of this quote unquote recent paper from last year. Was written together with some people from that at some point were associated with the Albert Einstein Gravitational Institute in near Berlin, Germany. So these people are experts on general relativity and black holes. And we had some interaction based on common interest, which I'll discuss here. And the result is this paper, which, like I said, came out already 1 year ago, but is still currently under review. I also have to apologize that maybe some of the participants have listened to me talk about related topics a number of times. So I apologize for the repetition. Okay, so right away, I want to give you the statement of the problem that we'll be trying to solve. It has a purely mathematical formulation, but it also has a physical interpretation. So this is which can explain interest in this topic from both sides, from people coming from relativity and those maybe interested in differential equation and the geometry of differential equations. So suppose that we are working on a Riemannian or in relativity Lorentzian or more generally pseudo-Riemannian manifold, G is the metric. We have the usual geometric structures there, Levi-Civita connection compatible with the metric, the Riemann curvature tensor of the connection, and so on and so forth. There's an equation called the Killing equation, whose solutions are vector fields, which generate the isometries. So these are infinitesimal solutions of the Killing equation. So this is the equation set to 0. Are so-called Killing vectors, and they correspond to infinitesimal isometries of the pseudo-Riemannian geometry that we're working on. Okay, now as a PDE, so this is a PDE, the Killing equation is an overdetermined equation, okay? Moreover, it falls into a more special subclass of overdetermined equations known as equations of finite type. I will go into that a bit later to explain what that means exactly. But that's just a side remark. Okay, so what's important here is that this is an overdetermined equation. An overdetermined equation usually comes with integrability conditions. So how are these integrability conditions expressed, or how can their essential properties be summarized mathematically? Well, consider the following definition. We call a capital C a compatibility operator, or sometimes I'll also use the term complete compatibility operator or universal compatibility operator for our operator K, the Killing operator, or it could be any other differential operator here. If any other differential operator, like small c here, which annihilates K, can be factored through this capital C, okay? This can be represented diagrammatically Okay, so the basic property we're trying to capture here is that whenever the operator capital K can be composed with something which annihilates it, such that this composition gives 0, this arrow has to be able to be expressed in terms of as a factorization through this arrow here. Okay, so this arrow has a certain universality or completeness property. And also, as a consequence, the composition of these two operators will be 0 as well. So this capital C, like I said, we call a compatibility operator, or for specificity, sometimes complete compatibility operator, to really underline this universality, the universal property of it. So the question that I want to pose here is, given a killing operator on a particular geometry, what is the compatibility operator, complete compatibility operator associated to it? And moreover, can we also find the compatibility operators of the compatibility operator itself, and so on and so forth? Okay, so what we would obtain as a solution to, as an answer to this problem, is a sequence of differential operators, each pair of subsequent operators composing to 0. So in some terminology, this is a complex of differential operators, and each subsequent pair of operators has the property that one operator is the complete compatibility operator of the previous one. Okay, and altogether we call this a full compatibility complex of the original operator, which in our case here is the killing operator on some pseudo-Riemannian manifold. All right, so this is a mathematical problem, it has a clear formulation, and one might ask whether it has one can solve it in some way. Okay, I will get to that in a moment. But first, I want to also add that in general relativity, the solution of this problem of the constructing compatibility complex has an interpretation. At least the first compatibility operator, this capital C, one could say, without maybe explaining the terminology too much, that its components constitute the complete set of local gauge invariant observables for linearized gravity on the spacetime MG. Okay, so spacetime is just a Lorentzian manifold. Linearized gravity corresponds to a certain linear PDE, which is obtained by linearizing so-called Einstein tensor, and that PDE has certain gauge symmetries, and then some differential invariants under those symmetries are called local gauge invariant observables. So I will not go in depth into that interpretation, but for people familiar with relativity, this should sound somewhat interesting. Okay, so there's a physical problem, there's a mathematical motivation. How can we actually go ahead and solve it? Oops. All right. So what are the possible approaches? And construction of compatibility operators is quite an old topic. And there are some approaches to it in literature. So I'll start with one, which is actually not good in this context, but it is whenever I talk about this work, it almost invariably comes up as a question. Why are we not using this method to obtain a compatibility complex? And again, I don't want, because this method doesn't really work here, I don't want to go into details, but for those who are familiar with it, there's something called the BGG Bernstein-Gelfand machinery or theory or method, which is based on representation theory, and it is applicable to certain overdetermined differential operators defined on homogeneous spaces. So spaces that have a transitive action by a Lie group, and in such situations, one may in fact construct a full compatibility complex for some particular operators using only representation theoretic machinery. But the particular case that we're interested in that we'll describe of a rotating black hole does not satisfy this property. So it's not a homogeneous space. There's not a transitive symmetry action on it. And there may be some generalizations of this machinery called curve BGG, but there's no obvious way for how to extract the compatibility complex that we want from it. Okay, so this is just a side remark. This approach does not work to solve the problem. There's also something called the Spencer-Goldschmidt theory, which is intimately connected with the formal integrability and involutivity of PDEs. It's very well studied. There are multiple experts on this theory in the audience that know it better than me. So one can, in fact, produce compatibility complex using this theory. It involves prolonging your original overdetermined equation to involution, computing Spencer cohomology of this involutive form. It is algorithmic. There are implementations of this in computer algebra, but it is not quite convenient for our purposes because the algorithm is quite laborious. So it involves a lot of intermediate large calculations as soon as the number of dependent and independent variables in your PDE exceeds very small numbers. Even though one can do all the calculations automatically using computer algebra, to do that, one first has to take your original differential operator and break it up into individual components in explicit coordinates. And unfortunately, that has the downside of destroying, or at least obfuscating, any special geometric or algebraic properties of your original differential operator. So the output can be the desired complex compatibility complex, but it is expressed in terms of these explicit coordinate components, and it's very difficult to extract any information or use out of it. So that's one downside. The second downside is that suppose that we get the output of this algorithm, which is a compatibility complex for our original killing operator. How do we know that this is indeed a compatibility complex satisfying these completeness conditions at each step? Well, the basic reason to believe that's true is that it's the output of the algorithm. Okay, so the witness to the property of the result being an actual compatibility complex is that it came out of the algorithm. But this is not very convenient if we just want to hand somebody this complex and want them to believe us, right? So we would like to give some proof along with the result, which could be perhaps verifiable by a human and not reduced to just running this algorithm again. All right, so, and there's another approach, which basically I found after working in this problem for some time. It's essentially pragmatic in nature. Okay, so that's the main motivation behind using this approach. And it consists of reducing the original overdetermined operator to a certain canonical form. And this is where it's important that the killing operator is of finite type, because so far I've only adapted it to that case. And in particular, one can find a canonical form for a finite type operator that looks like a flat connection on some auxiliary vector bundle. So the reduction is done through a certain reduction consists of a certain collection of data that one could call an equivalence up to homotopy. So it's a fancy name, but it's just a a collection of certain amount of data that can be interpreted as an equivalence between your original operator, the Killing operator, and a certain canonical form of it. In the canonical form, we already know the compatibility complex, and we use the equivalence to lift it to the original operator, and that's how we produce the compatibility complex for the Killing operator or any other overdetermined operator of finite type. So the advantage of this method is that so we can adapt the reduction to canonical form to whatever special algebraic or geometric properties our original operator has. And moreover, the construction comes together with a proof of its completeness. So we get some complex of differential operators, and we know that it's the compatibility complex for our original overdetermined operator by virtue of the existence of this data, which is the reduction to the canonical form given by this equivalence up to homotopy, which I'll explain in a few moments. And usually, especially because one was able to preserve some special geometric or algebraic properties in this reduction, the properties of this reduction of this data that are needed to prove the completeness of the final compatibility complex can be done by hand. So that's a pragmatic advantage. One downside of this approach is that it's not entirely algorithmic, but I've used it in already several cases, and pragmatically it does work. In terms of practical applications of these methods, sometimes some of them work, sometimes others, some of them don't work. So like I said, the methods 1 and 2 are applicable in some very special cases. For example, if we take geometries of maximal symmetry, then in fact, we can produce compatibility complexes in this way, and that has been done. So this is quite well known for a number of decades. But in other cases, the only method that I'm aware where a construction of a compatibility complex has succeeded has been using this third method of reduction to canonical form, which I introduced some time ago. Okay, so what is this method? Right, so it consists of several steps. So let me first make some remarks. So step 1 consists of the first remark, which is that the property of being a compatibility complex is preserved by what I call homotopy equivalences. All right, so let me explain what that means. Look at this diagram, so where all the data is neatly summarized. So the horizontal lines are complexes of differential operators, so sequences of differential operators that subsequently compose to 0. Okay, this is another complex of differential operators. So the idea is that one of them would start with our original overdetermined operator, the Killing operator. This one starts with some other operator, which would be this canonical form. Okay, so suppose that such two complexes exist, and they are related by these arrows. So each arrow represents a differential operator. Okay, the vertical arrows have to compose to identity up to a certain correction. Okay, this correction is expressed using these dotted arrows called homotopies. All right, so all these, this is summarized here. So the vertical arrows compose backwards and forwards such that they give identity up to certain corrections. And the form of these corrections are summarized here, and their form, once compared with literature on homologic algebra, justifies the name for that these corrections are basically 0 up to homotopy, and that the names given to these dotted arrows could be homotopies. So these vertical arrows could be called then chain maps between two complexes or chain equivalences up to homotopy. Okay, so the observation is that that I summarize this as this lemma is that if this data exists, this equivalence up to homotopy exists, and one of the two complexes is a full compatibility complex, then so is the other one. All right, so we've reduced our problem to first finding some canonical form for our operator that has a known full compatibility complex. Then, if we could build some complex extending our original killing operator and construct this homotopy equivalence, then we have proven that this complex on top is also a full compatibility complex, right? So now we need to complete those intermediate steps. Sorry. All right. So the next intermediate step is to reduce the amount of data that you need to build the equivalence of the homotopy between two complexes. All right. And it turns out that you can reduce it to the data containing just the first square. Okay, so the first square contains just our original operator, this canonical form, and the reduced amount of data needed to build this the start of this equivalence up to homotopy. Okay, they satisfy all the identities that I showed you before. So turns out that if we know all this information, then using the data contained in this first square of the diagram, we can build a candidate compatibility operator here on the top line. All right, so before we didn't know it, but we can guess what it is. And then we can, between these two operators, we can complete another square of the equivalence up to homotopy using these explicit formulas. And turns out, then by the previous remark, this proves that this operator is a compatibility operator for K0, which in our case is the killing operator. Right? And well, we don't have to stop here. We can iterate this construction if we know whatever the next operator that follows here, right? So we can build another square, another square, another square, and so on. If we know the full compatibility complex at the bottom and it has finite length, then we can build the full compatibility complex at the top, and we'll also have finite length. Okay, so that's the second intermediate step. So now we reduce the problem to just building this equivalence up to homotopy between our original killing operator and some canonical form. All right, so what does it mean in more kind of intuitive language that we apply to differential equations to build this equivalence? Well, perhaps people are quite familiar with the idea that one can map solutions of one PDE to solutions of another PDE using differential operators. Okay, and if there's a way to map these solutions back and forth in a bijective way, then the two differential equations that whose solutions we're comparing can be interpreted as equivalent. Okay. Now, on the surface, it sounds like there's less data in this notion of equivalence than in this notion of equivalence up to homotopy, which contains more of these operators. But it turns out that they're basically equivalent. So under favorable hypotheses, these identities that express the existence of two differential operators that map solutions of one equation into solutions of another equation bijectively. So when they can be reinterpreted when we apply these operators to just arbitrary functions. Okay, we don't have to apply these differential operators to just solutions. So differential operators can be applied to any functions. Okay, but then we have to reinterpret all of these zeros in the corresponding identities as being proportional to the equations that the corresponding solutions satisfy. So zero must become in some way proportional to the appropriate equation. But what does it mean proportional? So we make that more precise. Means that there exists some linear differential operator whose argument is the appropriate differential equation that replaces zero in the original identities that needed to be satisfied on solutions. Okay, so we've transformed this notion of equivalence, which is quite well established, into perhaps a more complicated looking but essentially equivalent notion of equivalence, which when summarized diagrammatically looks exactly like this notion of equivalence up to homotopy. Okay, so all of these operators fit into the in the appropriate way into this square. And as I mentioned before, it is at this stage that when we build all these equivalences, that we have the freedom of preserving any special algebraic or geometric properties of this operator K and whatever canonical form that we choose for it. Okay. So what is a convenient canonical form for a PDE of finite type, of which our killing operator is an example? So what is finite type? So finite type has the following definition. So the solutions of such an equation have the property that if you fix any point on the domain where they're defined, and then you fix sufficiently many or finite number of derivatives of that point of the solution at that point, then the solution can be continued uniquely into the neighborhood. Okay, so that's the property. So it basically guarantees that the solution space of this equation is finite dimensional everywhere, and it says the solution satisfies a very strong unique continuation property. Well, if you look at the fiber of initial data as that sufficient to determine the vector space, that's essentially the fiber of some vector bundle. Okay, and this unique continuation property can be expressed as a kind of parallel transport. Therefore, the solutions of the original equation can be thought as parallel sections with respect to some kind of connection, the connection that implements this, parallel transport. And because the solutions are well defined and unique, this connection has to be flat. Okay, so basically, you can also equivalently say that equations of finite type that satisfy a certain uniformity property, where the dimension of the local solution space is uniformly constant everywhere, can also be defined by those PDEs that are equivalent in the sense that I described just on the previous slide, to the equation of parallel sections with respect to a flat connection. And the flat connection is just some operator on some vector bundle with as many components as independent variables, and the components of this operator commute with each other. Okay, so given a flat connection, you can build a corresponding complex of differential operators, which you can call the twisted de Rham complex, where you start with the de Rham complex, which is well known as a compatibility complex for the exterior derivative on scalar functions. You replace scalars by vectors valued in this bundle on which the connection is defined, And you replace the components of all the de Rham and exterior derivatives by the components of the flat connection, and that defines this de Rham complex twisted by the connection D. And locally, you can choose coordinates on this vector bundle in such a way that it could look as just several copies of the de Rham complex, okay, for as many copies as the rank of your of the vector bundle in which this connection is defined. And the proof that the twisted de Rham complex is a complete compatibility complex for the flat connection operator is basically just a repetition of the Poincaré lemma for each copy of the de Rham complex that we have. Okay, very good. So just a comment about what is the rank of this auxiliary bundle on which the flat connection is defined in the case of the killing operator. And
Igor, may I ask
yes, of course.
a question? Well, if you have a flat connection, then there is well, you take its connection form, and then by means of the Nienhaus bracket, you construct a complex in a natural. Is it the same as you described here, or is it different?
So you said using which bracket?
With Nienhaus bracket. You take a connection form, it is vector variant form, and, and then the differential is the Nienhaus bracket with this form. Then you get a complex which is very close to the well, it is a sort of horizontal de Rham complex.
Yeah. So if your okay, if your connection one form vector value one form is 0, I guess you recover the just several copies of the de Rham complex, right? And I think that as long as the construction reduces to that case under appropriate choice of fiber coordinates, then yes, it should be equivalent.
Okay, thank you.
Yeah. Okay. All right. So this numerology is not very important here, so you can sort of ignore it. Okay. I just want to make a remark that this canonical form that we could feed into this three-step procedure that I showed to you on previous slides does not have to be a flat connection. Okay, it could be some other canonical form for which we know the full compatibility complex. It just so happens that in many cases the flat connection is a convenient form, but not always. Okay, but we won't really need to consider other possibilities here. Okay, just as a quick example to make things a little bit concrete, if we are in this case of maximal symmetry, which in general relativity carries the name of de Sitter or anti-de Sitter geometry or spacetime. So these spacetimes are characterized by the property that their Riemann tensor is given by the following combination of metrics times a constant. So alpha is just a constant, and in physics it could be called the cosmological constant or proportion to it. So there is a very concrete complex that you can build very explicitly. You can construct it using any of the methods I described before. You can build it representation theoretically, you can build it using Spencer-Goldschmidt theory, you can build this reduction to a flat connection form that I described just now. And up to some simplifications, you essentially get the same answer, which is sometimes called the Calabi complex. So you find that there are second order differential operators, first order operators, so involved of anti-symmetrization and so forth, so on and so forth. So if you were familiar with the Calabi complex, you might be comforted to know that it arises as a result of these kind of constructions. If not, then That's just to show that one can, in fact, explicitly implement these methods and get some concrete answers out of them. All right, so some more terminology. Okay, so now I want to come to the contents of our the actual work that is contained in this paper that that my talk is about, and that is constructing this compatibility complex for the killing operator on Kerr rotating black hole. So, what is the Kerr spacetime? So first I have to explain to you what that is. It is a Lorentzian manifold. It's a four-dimensional Lorentzian manifold describing a black hole. Okay, so you can imagine a black hole is some roughly spherical object sitting in the middle of a four-dimensional or three spatial dimensions. It has a boundary called the horizon, and we are going to consider just the outside of that boundary. Okay, so this looks like R3 minus a sphere in the center, and this geometry has an extension in time. Okay, so the outside of a horizon has the topology of R2 times S2. So S2 are these spherical shells, and R2 contains the radial coordinate and the time coordinate. Okay, this is just background information. We won't actually need any global properties of the spacetime because everything that we do is purely local. Okay, but on this spacetime, there's four-dimensional Lorentzian metric. It is asymptotically flat, so as you go out to infinity, it approaches Minkowski metric, and it is an Einstein vacuum. So the Ricci tensor of the metric is 0. So the explicit form of this of the metric is not important here. Okay, what is important is that well, it's been very well studied, and some key geometric properties have been identified that essentially uniquely fix what it is. So the first is that this spacetime is stationary, so it contains a time symmetry. Okay, so it can be written in a way where translation along the time axis is an obvious symmetry of the geometry. And it's also rotating, so there's it's not spherically symmetric. So when I said think of some roughly spherical object, I really meant it. It's kind of oblong spheroid. But there is a rotational symmetry about one axis. Okay, some particular axis, and there's a rotational symmetry around it. So basically, it means that the solutions of the Killing equation, which give you the infinitesimal symmetry, are two-dimensional, okay, spanned by the time translation and this rotational Killing vector. But there's more. So in principle, that is enough. You know, you can do some analysis and prove that these properties together, asymptotic flatness, essentially uniquely fix the spacetime. But it also has some other nice properties. So it has certain hidden symmetries, which are manifested by the existence of solutions to some special geometric equations called the Killing-Yano or Killing-Spinner equations. So there is a solution to one of these equations, which are essentially equivalent. I won't tell you exactly what these equations are, because it's not needed here. But the existence of such a geometric object essentially tells you that there will be two Killing vectors, and under certain conditions like asymptotically flat, it also implies that you are in this Kerr rotating black hole geometry. Moreover, the curvature tensor of this spacetime is not just some arbitrary four-index tensor with the usual symmetries of a Riemann tensor. It has some algebraic symmetries to it. And all of these special geometric properties are um, captured in a special calculus we call spinor calculus. Okay, so which is related to tensor calculus in a specific way, which I'll try to briefly describe in a moment. And I want to mention that these geometric properties of the space-time are not unique to Kerr. There's a larger but still finite dimensional family of spacetimes that share them, except for some of these properties. If you remove one or two of these properties, then there are spacetimes that will share the rest of the special geometric properties. For example, if you remove the asymptotic flat condition, then you get the so-called Kerr de Sitter or Kerr anti-de Sitter black holes, which are black holes sitting in some kind of cosmological setting. And if you add an electric charge, not just a mass, to your black hole, then you get so-called Kerr-Newman solutions, which can also be embedded in this cosmological background. Okay, we did not consider these more general geometries, but because they share a lot of the geometric properties with the Kerr black hole, then our methods could be in fact adapted to them. So we have not done it, but this could be done. Okay. Now I need to tell you a little bit about spinor calculus, because this is an essential ingredient in our recent work. And I'm not an expert on this. I had to learn some of this from my co-authors, who are indeed real experts on this. But the basic observation that one starts with is that there's this isomorphism between kind of the pointwise symmetry of general relativity, which is Lorentz transformations, or another name for the Lorentz group is the SO13 groups. So special orthogonal transformations with respect to a metric that has signature minus 1, 1, 1, 1. So this, it just so happens that in this particular case, the Lie algebra of this group is isomorphic to the Lie algebra of SL2C. So 2 by 2 complex matrices with a unit determinant. Equivalently, essentially, one can phrase this isomorphism as an isomorphism between the complexification. So this is a real Lie algebra, but we can complexify it. The complexification of this Lie algebra. So upon complexification, it becomes isomorphic to 2 copies of SL2C, and one of them is just 2 copies of the same algebra, but I put the prime on one of them just to distinguish one copy from the other. So SL2C has a very simple representation theory, interesting but simple representation theory, where there's a fundamental representation, which is a 2-component vector, complex vector, which is usually called a 2-component spinor, or just a spinor. Because we have 2 copies of L2C, we have 2 kinds of fundamental representations denoted in this way by this pair of integers, which for the fundamental ones just are 1 and 0, and 0 and 1. So whenever you see a spinor with a 1 index without a prime, then this corresponds to a fundamental representation of this copy of SL2C. And then whenever you see a spinor with 1 index which has a prime on it, that corresponds to the fundamental representation of this other copy of SL2C. So these fundamental representations have an invariant pairing on them, which is invertible, happens to be antisymmetric. So it means that you can use it to raise and lower indices. And there's also a primed version of this one as well. And because the fundamental representations are only 2-dimensional, when you take tensor products of these representations, you don't need to, all this machinery of Young diagrams and so on and so forth, like mixed, so tensor products symmetrized in mixed ways, always decompose into direct sums of irreducibles, where each irreducible is classified by two integers um, uh, corresponding to spinors with a certain number of unprimed indices, a certain number of primed indices, and symmetrized in each group, the unprimed and the primed indices. So any irreducible representation, I should say finite dimensional irreducible representation of this Lie algebra is of this form. Okay, so whenever we take products, contractions, symmetrizations, you can always re-express the result as linear combinations of these kinds of objects. Okay, and this can be seen as an advantage over tensor representations where you have to use some non-trivial Young diagrams. So this is done at the level of tangent spaces, and you can kind of do this covariantly at every point of your manifold, where instead of just thinking of some canonical SO13 Lie algebra, you can think of the Lie algebra of the special orthogonal group with respect to the metric at a particular point. Okay, so you can translate that pointwise to SL2C language, and this is done by constructing so-called spinor bundle on your pseudo-Riemannian geometry. And there's a way to translate the Levi-Civita connection into a derivative on spinors. According to the dictionary, I'll show you in a moment, a single tensor index can be replaced by a pair of spinor indices, one unprimed, one primed. And there's a way to translate all covariant differentiations into differentiations with respect to this so-called spin connection. And for those who are not familiar, here's a quick dictionary for how to translate representations of the special orthogonal group into spinor representations. So scalars are just scalars. Vectors, as I mentioned, correspond to this 1-1 spinor representation. Symmetric traceless two tensors correspond to 2-2 representations. So it so happens that two forms in 4 dimensions are not by themselves irreducible. They can be split into, especially when we're talking about complexified two forms, they can be split into self-dual and anti-self-dual parts, and each of them has a corresponding irreducible spinor representation, which are the 2-0 and 0-2. And another kind of tensor that is important in relativity is a tensor that having symmetries of Riemann tensor, but with 0 traces everywhere. So that would be, again, projected onto self-dual or anti-self-dual parts. So sometimes they're called self-dual, anti-self-dual Weil tensors, and they have corresponding spinor representations, which have 4 spinor indices without any primes, or all with primes. Okay, so these are the kinds of spinor representations that one can find while working with general relativity or linearized general relativity in 4 dimensions. Okay, so that was just general spinor calculus on any pseudo-Riemannian manifold. But when we are working with the Kerr geometry, then there's further special elements. So it turns out that there are special spinorial objects on the Kerr, adapted to the Kerr background. Okay, so the most important of them is this kappa, which satisfies something called the killing two-spinor equation, which once translated into tensor language can be identified as a self-dual or anti-self-dual version of the Killing-Yano equation for a two form. And basically the existence of a solution of this Killing two-spinner equation, and of course it has a complex conjugate analog with primed indices, guarantees that you are in this family of spacetimes, a finite dimensional family of spacetimes, which under the asymptotic flatness condition reduced to the family of Kerr black holes. Then you have the Killing vectors, which in spinorial terms have this index structure. So Xi is usually the time translation and zeta is the rotation, I believe. I could be wrong, it could be the other way around, but let's suppose that that's the case. You have background, you can always compute the Ricci scalar and Ricci tensor of your background geometry, and they happen to vanish. And there are spinorial versions of these, and they happen to vanish for Kerr spacetimes because we are in Einstein vacuum, as I said before. So the only non-trivial spinor associated with the curvature is the Weyl curvature, which is given by this 4-index spinor and a complex conjugate version of that. And these have some special algebraic properties, which are quite useful, but I don't need to go into here. And moreover, if you take derivatives of any of these special geometric objects, they can be re-expressed in terms of each other. So there's a kind of this satisfied kind of involutivity. So it's a very, very special structure that we have here. And moreover, we can construct so-called fundamental spinor operators, which take the derivative when applied, the spin connection applied to any irreducible spinor and produces another kind of irreducible spinor out of it, right? So whenever we take a derivative, we add one unprimed and one primed index. And so there are two choices that we can do with any new index. Either we can contract with an existing index, or we can fully symmetrize, including one of the new indices in the unprimed or the primed index groups. So depending on which option you take for each of the new spinor indices introduced by the derivative, you get a different kind of operators. So I believe these are called the divergence, curl adjoint, and twist spinor operators. And they have been developed, so their properties and their calculus has been developed into quite powerful machinery by some of my co-authors. So references to that can be found in our paper. And to give you an example of how this notation can be used, the 4-dimensional de Rham complex, so consisting of exterior derivatives on differential forms, can be re-expressed using the dictionary that I show here and these fundamental spinor operators in the following way. Right? So it's just some notation, but it's a very explicit translation of the de Rham complex in 4 dimensions into spinor language. Right? So these are 0 forms, 1 forms, 2 forms, 3 forms, and volume form, 4-dimensional volume forms. Now, recall that what we eventually want to do is reduce the Killing operator on this Kerr background to a canonical form, and turns out that the convenient canonical form is going to be a flat connection on the subbundle of the tangent bundle spanned by our 2 Killing vectors. All right, and as I mentioned before, and this connection happens to be flat, and it has a known compatibility complex consisting of 2 copies of the de Rham complex, which can be conveniently expressed in this way, just tensored with the 2 independent Killing vectors, right? So we have our canonical form for the Killing operator. We have its compatibility complex. So next, what we need to do is to build this explicit reduction. And this reduction relies on the special geometric spinners and the spin operators that I've just introduced. And it also relies on an explicit inclusion, projection, or orthogonal complement of the subbundle of the tangent bundle spanned by our Killing vectors. Okay, you can translate it into spinner language. So we have all of these operators, and turns out that well, one can explicitly build the reduction as an equivalence up to homotopy between uh, the uh, uh, the canonical form as a flat connection and our original Killing operator. Right. So how can this be done? So there's a very simple way to write down the equivalence maps that map solutions of the Killing operator to parallel sections on this auxiliary bundle, and that's just so this Killing operator is acting on the tangent bundle, and the flat connection is acting on the subbundle spanned by the two independent Killing vectors. So in one direction, this is just the inclusion of the subbundle spanned by the Killing vectors in the tangent bundle, and the other direction is just a kind of projection, and you can pick any projection, maybe orthogonal, maybe some other convenient kind of projection. And as I implied before, as long as these differential operators, which are just zero order operators, are bijections of solutions, you can reconstruct the rest of this diagram doing kind of factorizations, right? So you do some kind of composition, and you say, well, this composition is zero in solutions, so it must factor through one of these two differential operators, through D0 or K. And we have done this explicitly and built this equivalence diagram. And this was the most kind of time-consuming and work-intense part of the project because it involved a lot of symbolic calculus, which was done using some a special implementation of the spinor calculus by my co-authors in Mathematica. So they were doing all the calculations. I was very little involved in that part. Uh, just providing some guiding principles. So there's a lot of work that went into obtaining explicit and rather compact expressions in this language for the full set of the equivalence data expressed in this diagram. Okay, so it involves some guessing, verifying, but in the end, we managed to do it. And once we've done this, then we use the procedure I described before to extend this equivalence to full equivalence up to homotopy between two full compatibility complexes. Right. So this one is known, and this one we build step by step. Again, using relatively compact explicit formulas. And in the end, we were able to take the first compatibility operator K1 and explicitly compare it with another compatibility operator, which was previously published in Physical Review Letters. It was kind of an announcement. So this was published by two of my co-authors because they basically obtained that compatibility operator, say, let's call it K tilde, K1 tilde, through a kind of exhaustive brute force search. So they're trying out different ways to construct first order, second order, third order compatibility operator for the Killing operator. And they managed to do an exhaustive search essentially up to third order. Okay. And it seemed to them that basically they didn't need to do any more search. So they found everything that was needed to generate any other compatibility operators. But of course, how do you prove that, right? So they just did some exhaustive search. They stop at order 3. How do you know that you can satisfy this completeness property, that any other compatibility operator can be factored through yours? And this is where I got involved, and kind of very quickly behind the scenes, we were able to show that one can indeed take their compatibility operator obtained through an exhaustive search and factor it through the compatibility operator obtained through the construction that I outlined. And the construction that I outlined gives you compatibility operators with the completeness property, okay, by those few lemmas that I showed to you earlier. So because their compatibility operator is equivalent to the one that we constructed here, then automatically it is complete. And the proof of completeness is encapsulated in the explicit data of all the operators and their relations with each other that constitute the equivalence up to homotopy in between the complex that we build and the canonical form and their exhaustive search form. So that part also took, I mean, behind the scenes, we were able to do it quite quickly so that when the result was published already a couple of years ago, I mean, we were not in doubt that the compatibility operator that they were publishing was complete. And they claimed so in this paper without proof. But it took us some time to put all the details in place to produce a complete proof, which for the first time is given in this paper that I've been discussing. Okay, so I think I'm close to, maybe I already overrun my time by a few minutes, but I've basically summarized to you the work described in this recent paper, and I can basically conclude. So that's just a summary of what I talked about, a practical method of building compatibility complexes for equations of finite type, which in relativity, or of interest to relativity, comprises Killing operators on spacetimes of not only maximal symmetry, but also submaximal symmetry, as long as the rank of the symmetry is uniform over the entire spacetime. So the method consists of reducing to a canonical form, and once you have produced a compatibility complex for the original Killing operator, then the process gives a witness to the completeness properties of this compatibility complex by virtue of these small lemmas that and observations that I described at the beginning. So the most recent application, after some original applications that I gave as examples of this construction, is a rather non-trivial application of this method to the rotating Kerr black hole, which, as I showed to you, as I indicated to you, involved quite a bit of symbolic computation, but gives rather practical compact formulas, which with a little bit of effort can be checked by hand. Of course, one can think of how to extend these methods to other geometries, and this is being considered for future work. So I think now I will thank you for your attention.
Well, thanks a lot. Igor, I somehow missed it, or you didn't say it. Is it of maximal length? What
yes,
is
the complex is of maximal length.
Yes.
Finite type property.
Thank you. Other questions, other remarks?
Yeah, a question. So Igor, well, first of all, it's related to your your Simonovich question about length. Well, Kerr has two symmetries, right? And,
yes.
So why doesn't it reduce the length of the complex?
So the canonical form, as I said, is this flat connection on a rank 2 bundle. So rank 2 has to do with these two independent Killing vectors, right? But the compatibility complex on the canonical form is always full length because it's basically 2 copies of the de Rham complex, and the de Rham complex we know is full length. So it's if n, when we're in dimension n, then it has length n. So when we lift the compatibility complex of the canonical form to the original killing operator, because we have n non-trivial compatibility operators in the canonical form, they remain non-trivial for n in n slots in the lifted complex. So let me go back to this this slide here, right? So this slide, I discuss how starting from 1 square of this equivalence, right, and having 1 compatibility operator at the bottom in the canonical form, you lift it to a compatibility operator on the top line, okay, and you complete it to an equivalence, and you continue inductively. So if you have another non-trivial compatibility operator here, you have to lift it and you get another non-trivial operator, and so on and so forth. So canonical form has n non-trivial operators. The top line will have at least n non-trivial operators as well.
Well, in principle, you can also do the similar story with killing tensors, of course, right? And
yes, of course, yeah. So we haven't done it, but yeah, the same principle applies.
But the story is that, like, whenever you have killing vector, like it squares killing 2 tensor and so forth, if you get product of some killing tensors, you get another killing tensor of higher rank. So basically, there shall be relations between all those complexes. Yes, so you can, I don't know, some filtration quotients. So yeah, those actually, like higher killing tensors are much more interesting actually, like, because even like the existence is not clear. And especially that's important for Kerr, right? Because Kerr has quadratic integral, which is not a combination of any, of energy and linear.
Right. So for Kerr, in fact, yeah. So I mentioned that it has the special geometric object, which is an antisymmetric killing tensor. Okay, a killing 2 form, also known as a killing n 2 form, and it actually generates everything else. So it generates the killing vectors, and it also generates this quadratic integral, which is a symmetric killing tensor.
I mean, everything it's not clear. So do you state that actually any integral of any degree would be combination of those?
So for Kerr,
I don't know such statement.
I believe so. Yeah, at least degree 1, so killing vectors, symmetric degree 2.
That's known.
These are generated by this antisymmetric degree 2 killing tensor.
Yes, but there's no, like, okay, yeah.
Well, I'm just saying that it's not the other way around, right? So whenever you have antisymmetric killing tensor, you can generate these other ones. But when you have just a symmetric killing tensor, you cannot necessarily go the other way.
Yeah, it's very special. But historically, it was opposite. Actually, the Carter found the integral.
Yes.
Without killing Keanu.
Yeah.
So you mentioned some applications. I didn't understand this. Can you? So you said there's application to Kerr black hole. So what do you mean?
You mean on the conclusion slide?
Yes.
Well, I'm just saying that. So I just summarized in the first part of the talk where I described this method of producing a compatibility complex by reducing a canonical form, and I'm remarking that in our paper with Acksteiner, Anderson, Bagdell, and Whiting, we apply this method to, in an explicit case of the Kerr black hole, to do all the constructions. So that's.
I was thinking you mean that you can find application of this compatibility complex. Can you comment on this?
Right. So in general, as I mentioned on the first slide, there is an interpretation of the compatibility, first compatibility operator as this whose components generate all local gauge invariants for linearized gravity. So that's already something which is interesting in itself, I think, because often one is forced to work in a certain gauge to look at specific representatives from gauge equivalence classes of solutions of linearized gravity. And you might not be certain whether some property of that solution is an artifact of your choice of gauge or an invariant property. Okay, so plugging those special representatives into these gauge invariants might help you answer the question whether a certain property is invariant or gauge specific. Moreover, if you think of electromagnetism, so it's a theory based on one forms, okay, so-called vector potential. So with a known gauge symmetry. So one forms also come in equivalence classes up to additional of a gradient of a scalar. So it has a very similar structure, and a complete set of gauge invariants there are simply the components of the field strength tensor, which is just the exterior derivative of the one form. Now, the original vector potential, the one form, satisfies Maxwell's equations. Okay, these are fundamental equations of electrodynamics. This equation has this gauge symmetry that I described, and for that reason, it's not hyperbolic. It does not have a well-posed initial value problem because of the possibility of applying a gauge transformation which vanishes around the initial data. But the components of the field strength tensor, of the exterior derivative of the vector potential, satisfy a hyperbolic equation as a consequence of the original vector potential one form satisfying the Maxwell equation.
But where in all these arguments do you use anything from compatibility complex?
Well, one way to build this wave operator, so this hyperbolic equation satisfied by the by the field strength in electromagnetism, is by using the Hodge formulas for the Laplacian or for the D'Alembert operator, where you use exterior derivatives and these co-differentials. Well, the exterior derivatives have the interpretation as being operators coming from this compatibility complex for electromagnetism. Okay, so
but that's again interpretation, right? So it's a posteriori. So it was done by somebody, and then you
yeah. I mean, this was done, but I'm saying that we can use this analogy for now linearized gravity. So we can build this complex for linearized gravity on a particular background. And we can use this Hodge-like formula to build a differential operator acting on the invariants, which were also built using this compatibility complex. And so this new induced operator could have nice hyperbolic properties, but also have very nice properties related to the original linearized gravity equations. So this is one potential application which hasn't been exploited yet, but it could be exploited in the future.
Boria, are you satisfied?
Thank you.
Okay, more questions or remarks?
So maybe I would have a question. So small one, what do you mean on the slide we are seeing right now by observable? You say that the components of
I mean, physics has its own terminology, right? So
and I'm interested. What do you mean by that?
It's just the translation of the definition of a compatibility operator that I gave here. So you should take gauge invariant observable as kind of an atomic term. And it is any operator that basically has the property of this small c. It annihilates the Killing operator. That's all. That's all it is. So local here means that you know, this little c is not just arbitrary functional operator. It's a differential operator. So it involves local operations. And the complete refers to this factorization property.
Sure. And second question, you have shown the example with the flat connection, right? And you said that it's not necessary condition that the knowledge of compatibility complex is enough. So can you say a bit more about it?
So I will give you a very simple example. So let's go to this maximal symmetry case. So the Killing operator on the maximally symmetric geometry has this compatibility complex, so the Cauchy complex. Okay. Now, in fact, in some applications that I gave in the original paper where I presented this reduction to canonical form method, I use the knowledge of this complex to build a canonical form, which is not just a so I have some particular space-time whose geometry contains something of maximal symmetry. So not the whole space-time is not a maximal symmetry, but suppose it's spherically symmetric, right? So the spheres are maximally symmetric, right? So what I had done is reduce the Killing operator on a spherically symmetric space-time to an operator which has multiple components. One of the components, or some components, are connection-like, but other components basically correspond to a Killing operator on these spherical orbits. Okay, so then I build a compatibility operator for this canonical form in a hybrid way. So part of it is built using the twisted drum complex, but part of it is also built using operators from the Cauchy complex and, you know, mixtures between them. So I hope that's more or less clear.
Yeah. Thank you. And maybe a last small question. Yes, so if you are having the two complexes and say the bottom one is the one you know and the upper one the one you want to construct, then the upper one is always the same length as the bottom one?
Basically, yes, because you do this construction inductively, and whenever you end up with 0 as being the next operator, you kind of stop.
And can the construction be infinite?
I mean, so going back to this well-known Spencer-Goldschmidt theory, so it proves that for any overdetermined PDE, of course, you have to assume some uniformity properties of the symbol. There's an upper bound on the length of the complex that can be achieved. I mean, of course, you can have longer examples, but any longer example can be reduced to one which has at most n terms. So n is the number of independent variables. So the drum complex or twisted drum complex is an example of maximal length.
Thank you.
Okay, more questions? Igor, thanks a lot.
Thank you again.
Thank you, everyone, for participating. So we meet in a week, and the next talk will be by Boris Kruglikov. You're welcome. Have a nice week. Bye-bye.
Bye-bye.
Okay. Thank you very much.
Thank you. Bye.